All right. Hi, everyone. Thanks a lot for coming. I'm very happy to be here. And as you probably guessed, I'm going to be talking about PyTorch. So yeah, I'm one of the people who basically started it, although like a lot of people have joined over the year. It's a project that's already like 2 years old. So we've gathered a pretty significant amount of contributors, which we're really thankful for. But yeah, basically we've met here. I want to announce, like we've announced it before in fact, but like I want to talk about the new things that are coming in PyTorch 1.0. So just to kind of sample the audience, how many of you actually do know what PyTorch does? Like what can you do? You don't need to know the exact API. If you could raise your hand just to kind of give me an idea. All right, so we have a fair amount of people. So I'll just like, for those of you who don't, I'll just really quickly go over the stuff that you can do with the library. I don't really have time because we have only half an hour, so I'll try to make it quick. Whoops. Oh no, those are my older slides. We didn't change them. Can we swap them right now, or? Yeah, sorry for the interruption. There have been some changes, but yeah, exactly. No, no, no. There was a there was an email. All right, great. We see the old logo, so we're back on track. Yeah, so basically, those of you who like know PyTorch probably know it as a deep learning framework. I don't really have like a lot of time to get into this. Basically, it lets you implement a lot of like recent deep learning methods, but also more general machine learning methods. If like I'm going to give you a like 3-minute kind of overview of what it is, it's really much simpler to think about it as something as Numpy, which probably more of you know. So basically Numpy is like this library that lets you have array objects in Python. So like it kind of generalizes lists in Python to like higher dimensional objects. So you can have whole matrices of objects, in particular numbers, or you can have higher dimensional arrays and do some manipulations on them. And in particular, if you have arrays of numbers, it will store them in a very efficient like native data format for the computer. So like you can actually do some data crunching really fast. So basically in here we allocate like one array that's like 2 by 3, then just like create another like wrap a scalar. You can also wrap scalars, you can add them, it will automatically like expand the scalar to match the sizes. You can like take the 2 columns out of the array. You can do some, linear algebra functions on this, like you can do matrix multiply, that's what the add does. You can sample random matrices. So there's a lot of functions basically you can do, and ultimately at the lowest level, PyTorch is exactly this. So you can also see that like there's a lot of parallel in the APIs because like that's ultimately like how people are used to dealing with data in Python. So, but ultimately, of course, just redoing NumPy would be kind of silly. So obviously there are more features that are there. So in particular, it does integrate with NumPy very well because that's kind of the language that every single package speaks in Python. So basically there are functions that let you kind of get a NumPy array from a PyTorch tensor and vice versa, convert it back, so you can kind of use PyTorch like as part of your program, while everything else kind of uses any of your favorite Python libraries, like for communication, for plotting, whatever. Like it just works and it integrates nicely, and what's important about this is that it's actually extremely cheap. So the cost is completely constant, it doesn't depend on the array size, and that's because the data in fact is shared. So we're only kind of reallocating some objects, but the data that like you can read from the array and that you can manipulate via the array is exactly the same. It's in exactly the same place in memory. All right. Whoops, we've got some freezes in here. Anyway, so Yeah, so one of the features that actually differentiate PyTorch from Numpy is, for example, accelerator support. And accelerators are really important, especially for machine learning, but also for data science nowadays. So basically, when I'm talking about accelerators, I'm really thinking mostly about GPUs, which a lot of you already have. Even consumer-level GPUs can do a really fair amount of compute those days. Like, in particular, those array operations map to GPUs very well, because like GPUs are extremely parallel machines, um, and so it's really easy to transfer those programs and actually execute them efficiently on them. And just to kind of give you an idea, again, I don't have a lot of time to go over the API, but like that's everything. This runs on CPU, this runs on GPU. So you can use the to function to move between devices. You can specify what device some kind of array should live on, but basically all of the operations, all of the APIs are the same. So it's really easy to have like functions that are completely agnostic with respect to what device they run on. It only matters like what kind of inputs do you supply to the function, and that's where all the compute will be happening. So you can even use multiple GPUs if you have. All right, and another really important feature, I think, is really high performance and efficient automatic differentiation. And so that's basically something that lets you implement an arbitrary function, and you don't really need to bother like writing derivatives by hand. You just kind of ask the system like, oh, I like had those inputs, I computed this output, now tell me what is the exact derivative with respect to those inputs, right? And so this is especially important in machine learning because it actually lets you, like gradient-based optimization is something that basically powers most of deep learning right now, and also like widely appears in other domains. But also AD is like used in finance or in like some engineering problems, like some physics simulations, for example. So PyTorch also arrays, basically arrays are kind of the first class object in here. All of them support automatic differentiation. You kind of need to give us some hints about what you will want to differentiate and what not, because it unfortunately increases some overheads. But in general, like in here, you see that there's like a regular polynomial function that you could write in Python. There is nothing special, like no particular annotations in the code. And then you just use this torch autograd grad thing, and you give it the output of the function, you give it the input, and you basically get something that like exactly matches the simple formula you could get by differentiating this function by hand. The laptop is really surprised when I'm switching the slides. Anyway, yeah, so that's kind of all the time I have, unfortunately, to give you the overview of the library. So hopefully you kind of get an idea. Now I wanted to move on because there's really a lot of stuff that we've put into 1.0 that I want to cover. And yeah, hopefully we'll make it on time. So yeah, so basically 1.0, something to note is that it's a release candidate, which means the release is not fully out yet. You can actually download it. You can actually download it, and you can play with it. We don't call it stable, not because the release candidate is unstable, but because like we're still kind of making changes to it, and like you might still find some minor errors that we're kind of tweaking, before we kind of really reach the final point at which we'll freeze the binary and like the actual code that you will be running. And that will happen in a few weeks. We're targeting basically the beginning of December, hopefully sometime around NIPS. So yes, you will be able to download the full version like on all platforms relatively soon. Now we'll wait for the next slide. All right. Yeah, so something that's been really big about this release was basically that PyTorch, as you saw, like looks pretty much like Numpy, and this is something that basically made it really appealing for a lot of researchers. And in fact, the like main driving force behind PyTorch's popularity was like a crowd of researchers who started using it and who really liked it. And basically that's because like that's exactly for the reasons why Python became kind of dominant in data science, right? Like it's really easy to iterate on various pipelines that you're building. It's really easy to kind of swap out some blocks in the middle, change preprocessing. It's like just a matter of a few lines of code, and like you have a lot of higher level helpers from different libraries that you can kind of compose very easily. So this is something we really emphasized, and like again, we really wanted to integrate with everything very well. So the research side we kind of had covered. Something we didn't had covered was something you can call deployment. And at this point, it's really important to kind of clarify what deployment do I really mean. because like it's not like PyTorch was completely unsuitable for production. In particular, there are people who are running it in production right now, and were running it even a few months ago, before we even announced 1.0. Like it's completely fine to run Python in production in many cases, right? Like Dropbox or Instagram basically are still using Python for like certain parts of their architecture. However, there are still cases where like this is definitely not something that you would like to do, right? Like if you're packaging a mobile app, like Python interpreter kind of weighs, you know, more than 10 megabytes probably. That like adds to your binary size. This adds overheads because like it's not a particularly fast language, especially if you have a weak CPU. So you really would like to run this without the overhead of the full, you know, Python programming language in there. And so to kind of address those problems, something that the like mode that runs in Python, I'll be referring to as eager mode, and that's the thing that, you know, it's really simple to write and debug, that basically is really good for research. You can iterate quickly. And in fact, we believe that like most of the time that people do will be spent in this part. Like you will ultimately spend at least a few days or weeks kind of trying to figure out the solution. And once you reach the final solution, you'll kind of want to package it. So then you need some kind of tool that lets you take the final product of your research and just distribute it somehow in the sense of deployment that I meant. Like if you can run Python, that's great. You don't need to do anything really. And so something that we've added is basically called the script mode. And script mode, like kind of underneath, at the lowest level, is really a new programming language. Although that shouldn't really scare you, because that's really a programming language that uses exactly the syntax of Python and uses a subset of Python semantics. So like if you write PyTorch script code, basically you could run this as Python code and it would run exactly the same. So like there are very little boundaries between them. So you're kind of still programming Python no matter what you do. You're limited to this subset, but the benefits you get is that we can actually extract, like it's a much simpler language, so we can extract a very concise representation that we can serialize and later send to a mobile device, for example. And we actually like have more complete information about like what kind of array manipulations you're doing inside your program, so we can also apply some optimizations that would be really annoying to apply by hand, especially like do some optimizations on the derivative code. So just to give you an idea of like what can you do in this subset, so types that are supported, that's probably like most informative. You can obviously work with tensors, integral and floating point scalars are fine. Basic control flow if conditionals, while loops, for loops work. Print statements work, strings work, tuples of anything, lists also nested, basically polymorphic lists are there, and function calls. So it's a relatively limited language compared to like whatever Python can support. But if you think about it, like really, this is definitely enough to like express most of machine learning programs. And in fact, we've been using it with like relatively, with like some successes, which is really good. All right, so now the question is, you kind of iterated on your program, you have this eager program that you use to train your model. Now the question is, how do you take the like result of your work and actually package it? And there are two ways basically that we provide you to do that. So the first one is TorchIt trace, and basically something that's really good about this function is that it actually doesn't require any changes to your code whatsoever. So you can still use the full power of Python. The downside of this is that it actually like you have to give it a function that you want to kind of recover, and you have to give it an example. And it will run this function once, and it will kind of record every single PyTorch operation you do along the way, right? So the downside is that it actually doesn't record control flow at all. So this is like a single list of instructions that happen. So like if you have an if conditional, only the like branch that was taken in the example will be present. We'll never reevaluate the condition again. If you had a loop that executed 4 times, it will always execute 4 times. We'll never check the condition again. And we also like don't check for this in your code. So like if you accidentally produce something that's not like whatever you meant, that's unfortunately on you. And you might think that actually sounds dangerous, but this is actually very useful in a lot of use cases. Like if you take convolutional neural networks, basically, which will appear in a moment in here, So this is a picture from the Residual Learning paper. So basically, most convolutional neural networks kind of have this fixed structure, right? So they're this like kind of mathematical object that like always computes a function that's like specified kind of like this. So it doesn't really matter how do you like what code do you use to describe this structure. What's important is that you actually implemented every single block in here is basically an operation that's done inside the network. And so what's important is that if you like use PyTorch functions to implement those, we'll recover exactly the same sequence as it appears in here, right? So, and as an example, like you can have for loops as part of your program and like have it being completely fine. So this is a dumbed down version of the network I've been talking about. So if I were to implement a network like this, I would probably just have a list of those blocks. I don't want to get into the details of like what's on the top of the slide, but every single element of this list is kind of a single block that you saw in the picture a moment ago. And basically then the whole model would be like just iterate over those blocks and kind of apply them in a sequence, right? And so if you were to trace it, it would actually evaluate to something like this, and yeah, so it will kind of fix the length of the list, but ultimately the structure of your model stays the same over the whole training, right? So like it might depend on some command line parameters, you might be dynamically specifying the number of layers, but while you're training the model, you probably won't be adding more of them. And if you add more of them, you can actually retrace it and like keep training again. But like as long as it stays constant, it's fine, and you can actually export this model just fine. In particular, if you go to the Torch Vision package, it's a package that we have with like a lot of utilities for training models for computer vision problems. Basically, it provides some common data sets, some data loaders, and pre-trained models. So if you take any model, pre-trained or not, from this package, you can safely trace it because they're all basically based on this static graph approach. So it doesn't really matter like whatever code we use to implement them. And the other one is TorchIt Script, which is exactly something that lets you write basically in the script mode. So you're still writing Python. We do static it's a function decorator, so you can kind of mark the functions you assert to be in the subset of Python that we care about. And we do static analysis on those functions, so we can correctly recover control flow that's happening. We will be actually like running loops as many times as they should and like calculating how many times we should run them. The downside obviously is that you're still restricted to the subset. So like you can't do arbitrary things inside. And the example that's not my iPhone, but the example that like fits the script really well are recurrent neural networks. So in particular, recurrent neural networks, you can treat them as sequence-to-sequence models. So you can have an input sentence in one language and output another sentence in a different language, right? Because you have a translation problem. And sentences obviously vary in length, right? So you will want to run a different number of steps depending on what kind of input you got. So in this case, you couldn't really use trace because you would fix the sentence length. But you couldn't use trace, but you can use script, which will correctly recover this. And in fact, in here, like, provided you have this LSTM cell defined, you can see everything that you need to write out an RNN in PyTorch and even in PyTorch script, which is completely exportable. And the nice thing about those two functions is that they actually mix seamlessly. So if you have kind of a large, complicated model that's ultimately almost fixed and that like just looks kind of like a CNN, and except like in some part in the middle, it kind of has some component that requires some dynamic control flow, you can just script this component. And in fact, in this case, script, when it detects, trace, when it detects that it hit a scripted component, it will not trace it. It will just use the scripted kind of description, and it will actually have control flow in the final thing. And also, script supports function calls. So if you call something that's been traced before, from the surrounding scope, that will also be registered as a proper call. And what I mean a proper call, it's also important to say that actually script can also call back to Python, which is very convenient. Because like we don't really want you to kind of go on a long adventure of taking all of the model code you have and transferring it to this subset and hopefully getting it kind of to work. And after 2 days of work, you finally test it, and then you made a mistake somewhere along the way, and that would be basically a usability nightmare. So instead, what you can do is you can actually change your implementation function by function, checking every step along the way that everything is still fine, that everything still works. And also, if you kind of have a model that you exported, but then you kind of want to go back to the research cycle, it's still fine to like remove a few of those annotations and just, I don't know, start using Numpy or any other Python library inside, so that we won't complain that you're using something, outside of the subset, but you can still run your Python program in particular. And yeah, and the descriptions we get kind of look like this from the more compiler-oriented view. If you're interested. Basically, you can also inspect this like for tool for visualization of like whatever your models do, but like you don't really need to completely do that. Like it's kind of for as a more advanced usage. And the important part is that like I talk about export, so there's basically a single method which is like you can call on the a scripted function or on a traced function. You can call .save, and it basically will dump a file on your disk. Which you can later load, like using this single top line in here. You can basically load it back in C++, and we also have a C++ interface that pretty much matches our Python interface that I'll be talking about it in a moment as well. And so in particular, we have a pure C++ binary that we kind of allow you to use, that you can like integrate into your mobile apps. It's much more lightweight. It doesn't really require the Python interpreter. It has its own interpreter for those programs that we like support in this subset, which is much faster and much more efficient than this. And also, so that was for export mostly, but like I also talk about optimizations, and so something that we're kind of trying to help you with is, so PyTorch kind of comes with a lot of operations built in, and if you like, if something you want to do exactly matches the operations you have, is basically like they're optimized kernels written for them, so we'll use those, and that will be really fast. But if you write it yourself in Python, it will like be 5 times slower. So JIT is kind of aiming to help with that. It will like attempt to redo the optimizations automatically for you. The like roadblock sign in here is because that's not really finished. Like we're not promising magical gains at this point. Like it's 1.0. This is a very new feature, and we've been mostly focusing on getting kind of the usability right and not actually the optimization. But like on some LSTM variant, so it's a recurrent network that we've been benchmarking. It's actually like a 3.2x speedup, which is pretty good. Anyway, so another feature that's really important, I think, for if you want to use this in resource-constrained environments, are extensions and interface. So actually, PyTorch lets you take both. This is for research; those are extensions. So PyTorch basically lets you kind of bind CUDA kernels and custom C++ code into Python without having to go through a lot of pain of creating a completely new package and like using Python C API for extensions. And basically, so in here, there's like a function that dispatches some CUDA kernel and like multiplies one of the input arrays by 2. And everything you need to actually bind this to Python from C++ are those 3 lines. So we use PyBind 11, which is a really convenient library. So yeah, that's everything you need to do in C++. The problem with C++, obviously, is that at some point you actually need to compile it. And so we do provide some helpers for this as well. So there is a setup tools-based method, which is for if you want to actually distribute this. But if you just want to kind of quickly hack on a file, there is basically a one-liner where you kind of provide a list of files you want to compile, and that will like set all the appropriate flags and call into your compiler and load the module into Python. So then you just like call .compute, which is exactly the name we used to expose the function on the previous slide, and like and you can just provide arrays, or like in fact it works with like vectors of integers or tensors or nested or whatever you really want. So it's really convenient. And the interface is in beta, but you can try it out. Like even in 1.0, this will be in beta, so there might be some slight changes that we'll be doing to it. But basically the idea is that like this is an example of how would you write a neural network in Python using PyTorch, and this is how it looks in C++ right now. So it's like relatively close. You can see that it's mostly syntactic differences. In fact, if you were to look at a training loop, that's how it looks in Python, and that's how it looks in C++. So those are like exactly, you just change like dots to colons and like change the syntax of the for loop, and it's pretty much that. So like if you're doing some RL research, if you have like doing some robotics, you just have a C++ application, you don't want to figure out how to integrate with Python. Now you'll be able to just like have a pure C++ code base to do all of their kind of training and development. And there are a lot of packages that we've already ported. So there are helpers for building neural networks and machine learning models. There are gradient-based optimizers. Obviously, the AD, so automatic differentiation and accelerator support work in C++ as well. There are data loaders that like efficiently parallelize data loading, so you can like always have something to train on. There are serialization utilities, utilities for integration with Python, and there is the JIT compiler that we developed, which is exactly this like Python subset, this script mode. And the last feature that I want to talk about, I don't have a lot of time left, unfortunately. Basically, we did a kind of distributed backend overhaul. So it's like a completely new code that interfaces with different backend that like reinforces new abstractions. In particular, it emphasizes asynchronous operations. So we do keep API compatibility with like older versions of PyTorch, but you can specify some flags that tell us to kind of run some jobs in the background, and you get kind of future objects which you can wait on, right? So you can kind of interleave multiple transfers. You can have multiple groups that work using different backends. So you can use one library for exchanging information between GPUs. You can use another library to exchange information between CPUs and different nodes. And also there are some performance improvements, and in particular the new API that like lets you use multiple backends. It also lets you implement fault tolerance, which is something we didn't support previously. And also instead of fault tolerance, you can actually like leverage the same API to also implement elastic sizing and like use the on-spot instances when they're cheaper to kind of scale up your working group and like make your training progress faster. And kind of the last bit of news is that like those of you who kind of follow PyTorch news, Cafe 2 is merging with PyTorch, which is really great because Cafe 2 has a lot of great kernels, especially for mobile, and like the Cafe 2 team has like a lot of experience in running in those resource constrained environments, so we're working with them to kind of bring them together and like use the research side. So the API will like remain whatever I showed you, but like a lot of the backend bits especially will come from Cafe 2, where they have been heavily optimized over the years. So yeah, that's everything I have. PyTorch is really like, we're really a community project, like everything's happening open source. All the development is happening on GitHub, basically through pull requests. It's supported by multiple entities, both academic institutions, both academic and corporate. And yeah, we have really active community. As I mentioned, we have quite a bit of contributors and very active user forums. So if you have any trouble, you can just go there and someone will surely help you. And yeah, so I hope to see you somewhere on the forums or on GitHub, and thanks a lot for coming.